Okay, this is a problem from, sorry about that, fall of 2011, exam number 3, fall 2011, exam 3. So this is the first problem. And we're looking at a rod. Okay, so that's usually going to let me know it's probably axial. And it's fixed at A and C. Usually when I see it's fixed on two ends, it's telling me it's probably going to be indeterminate. Okay, has a cross-sectional area, and I know it's the area because of units, 10 inch squared. Again, always go back and look at your units. It's given in inches squared, so I don't confuse it with a radius or diameter. We have a 700 kip load applied, and I can also see this is a normal force versus torque. Okay, it's not torque. It doesn't have that double-ended, double-arrowed. Okay, it's applied at B. And we want to find the maximum stress in the steel rod and the displacement at B. And we have these stress strain curves. So I know the yield stress is 36. I have E, and I have the strain at yielding. Okay. So the first thing that I'm going to do is I am going to, sorry, I keep missing stuff. I keep laying stuff down. I don't know where I lay it. So the first thing I'm going to do is I'm going to go ahead and write down that I have an area of 10 inches squared, and I have a yield stress of 36 KSI, and an E of 29,000 KSI. Okay, and if I'm dealing with normal stress, then I'm going to have P over A. I could have delta is PL over AE, and stress equals E times strain. So there's my relationship. Okay. Here's my relationship. This should say E. Okay. So, and I know that strain is delta over L, stress is P over A. It's all one big happy family. Okay. So I need to determine, if I'm going to determine these internal stresses, so I know the stress from A to B has to be that internal force from A to B divided by area of A to B. And I know that the stress from B to C has to be the force in B to C divided by area of B to C. And this is going to have to come from that reaction at C. And this one's going to have to come from that reaction at A. So if I can find my reactions, I can get those internal stresses. And looking at this, I'm guessing I probably have some tension over here and maybe some compression. So chances are I have reactions that are pushing here at the wall, pushing this way, we're pushing back. So I have my reaction here at the wall, and I have my reaction here at this wall. So I'm going to start with equilibrium, and I'm going to sum forces in the x direction. And when I do that, I'm going to get that my force at A plus my force at C equals 700 kips. And some of you all have already figured out the ratios, that if this is the same material with the same cross-sectional properties, the same area, the same everything, then this is going to be a ratio just like what we had in statics with point loads, with shear. So if I know the whole thing is 4, then I can take 700 divided by 4, okay? So that means I'm going to end up with that the P of A should be 175 kips, and P at C should be 525 kips, using our ratio rule. And remember that only works because it's one solid piece of the same material with the same geometry. But I kind of know where I'm headed, okay? So I look at equilibrium, and I have too many unknowns. I can't sum moments, I can't sum forces y, I'm kind of stuck. So now I can go back and look at compatibility. And I know that for my compatibility, the deformation of A to B, okay, I could say delta AB minus delta BC equals 0. Okay, delta AB, it's in tension, minus delta BC, it's in compression, equals 0. Or I know that they both equal each other. I put that over, they're both positive. As one is moving to the left, or to the right, the other is moving to the right, okay? And I also know that delta, okay, delta, because I have all my equations written up here, is going to be P of A, length of AB, area of AB, E of AB equals P of C, because that's BC. Remember we said P of C is the same as BC, L of BC, area BC, E of BC. And you'll notice, you know, a lot of these problems I don't put numbers in until I kind of work through variables. And the beauty of this is all one solid piece, so the area and the modulus of elasticity, they go away. I can divide them out. And I'm left with this ratio, which we already talked about. Okay, I have that PA is to 3 feet as PC. Okay, PC is to 1 foot. And so it makes this nice little ratio, and we're going to see that this really does work just like it did for shear. So I can come back up to this equation. PC equals 3 PAs. So equation 1, I have PA plus PA times 3 equals, okay, so I plug that in, equals 700. And then I'm going to get 4 PA equals 700 kips. And I'm going to find that PA equals 700 divided by 4. It equals 175 kips. Okay? And if this equals 175 kips, well, I already told you, PC equals 525 kips. Okay? And we could plug that back into our delta equation, or we could plug it into our equilibrium, and it's going to hold true. If I put 175 in here, okay, then I'm going to get this is 525. If I put 175 in here, I'm going to get 525. So now I have to make sure that we haven't yielded, because these equations are only good in the elastic region. So I have to keep checking and checking and checking to make sure that I haven't yielded. So our stress of AB equals force of AB divided by area of AB. And I have 175 kips divided by 10 inches squared equals 17.5 kips, which is less than 36 KSI. Perfect. Okay. Now I have the stress of BC, which is the force of BC. Area of BC equals, okay, so I have 525 kips divided by 10 inch squared, and I get 52.5 kips, and oh, that is not less than 36 KSI. That is sad face, okay? So now we have to go back to, if you watched one of my other videos, we're like Mike and Sully. Me and my friend Mike and Sully. I'm Sully. I have a friend Mike. I really don't have a friend Mike, but if I did, I could be Sully. And the two of us are working together to keep this system in place. Okay? And again, I only have so much capacity in my body. Okay? I can only go up to 36 KSI. So once I reach this 36 KSI, once I hit this magical load that causes me to be 36 KSI, Mike has to kick it into gear and start taking up my slack. So Mike not going to be allowed to carry just 175 while I try to carry 525. That's just, it's not going to happen. So once I hit my yield stress, we don't want to go there. Okay, we don't want to go there. This guy over here is going to start picking up the load. So, if the maximum stress I can have is 36 KSI, well, stress equals force, okay, force in BC divided by area of BC, and I get then the maximum force we can have in BC is 360 kips. So forget 525, I can't do it. I can't carry 525, but I can carry 360 kips. Okay, so if I'm carrying 360 kips, that means I am at yield stress. So the stress that we have in this member right here is 36 KSI. It is at yielding. Okay, this is stress BC. So how do I find stress AB? Well, if I can only carry 360, then force AB has to be that original 700 kips minus 360 kips. So the force in AB is 700, enter, 360 minus 340 kips. So look at that. AB went from carrying 175 to 340. Okay, it 340, because me sitting over here, I can't carry the team by myself. 36 KSI is all I can do. That's 360 kips, and I'm out of here. That's it. That's all I can maintain. AB's got to pick it up. So now if I want to find the stress in AB, I know it's simply the force in AB divided by the area. The force in AB is 340 kips. The area is 10 inches squared. So I get 34 KSI. And again, that's less than 36. So we're good. We don't have like the next issue when everything starts to yield. Okay. So now that we found our yield stresses in our two segments, I want to find the displacement at B. Well, because this side has yielded and it's wanting to go beyond yielding, and we're using this side now as our control, we have to use the displacement from A to B, because it's still in this elastic region, to calculate what our deformation is. Okay, so we're going to take the force in AB, length of AB, area of AB, E of AB, and that force that I had was 340 kips. Its length is 3 feet. We don't want feet. Multiply it by 12. Its area is 10 inches squared, and it's 29,000 KSI. So I'm in units of kips, and a bunch of inches. So if I multiply this out, I get 340. 3 times 12 times 10 divided by 29,000 divided by, and I get a delta from A to B of 4.22 times 10 to the negative 2 inches, or you could write that as 0.0422 inches. So that's how much we're moving from B towards the left. We can't see it, 0.0422 inches. Okay.